Understanding Menus, Fitts Law, and Modern Interaction Techniques, Part 2. Narrated by Eric Vati. Here is an overview of this lesson. Before the era of Windows, icons, and point-and-click, software relied on textual menus to let users choose commands. In those environments, a menu might be a simple list of options printed on the screen, each preceded by a number or letter. These menus were essential because there was no mouse to click on graphical elements, so the keyboard was the primary interaction device. Even after graphical interfaces appeared, early Windows versions kept non-GUI menus for tasks like boot configuration and system utilities. The drawback was that such menus occupied a substantial amount of screen real estate, forcing users to scroll or switch windows to see the underlying content. This limitation set the stage for more compact, dynamic menu designs that we see today. Graphical user interfaces introduced the concept of drop-down menus, where a single bar expands vertically only when the user clicks or hovers. This approach dramatically reduces the permanent footprint of menu items, allowing the main workspace to stay visible. Pop-up menus, also known as context menus, appear directly under the mouse pointer when a user right-clicks, offering relevant actions without cluttering the interface. Web designers borrowed these ideas to create navigation bars that expand into submenus, preserving screen space on devices of all sizes. By showing options only when needed, drop-down and pop-up menus improve discoverability while keeping the visual design clean. The evolution from static lists to dynamic menus reflects a broader trend toward efficiency and user-centered design. Fitts' law emerged from early research on human psychomotor behavior, seeking to quantify how quickly a person can move a pointer to a target. The law captures the intuitive observation that larger, closer targets are easier to hit than small, distant ones. Although originally studied with mechanical devices, the principle holds true for modern computer mice, touchscreens, and even stylus input. Designers use Fitts' law to estimate how long a user will take to select a button, menu item, or any interactive element. By understanding this relationship, we can arrange interface components to minimize effort and error. The law thus provides a scientific basis for many of the heuristics we apply intuitively when crafting user interfaces. The formal expression of Fitts' law states that the movement time, mt, equals a constant a plus a factor b multiplied by the logarithm base 2 of the ratio of twice the distance, a, to the target width, w. In practical terms, a represents how far the cursor must travel from its starting point to the center of the target, while w denotes the size of the target along the axis of movement. The constants a and b are determined through experimental measurement for a given input device and user population. The logarithmic term, often called the index of difficulty, grows as the distance increases or the target shrinks, reflecting the added challenge. This equation allows designers to predict the time cost of different layout choices before implementation. By plugging realistic values, we can compare alternatives quantitatively rather than relying on guesswork. When a cursor moves toward the edge of a monitor, it cannot pass beyond the boundary, which effectively enlarges the target area along that edge. This phenomenon means that a button placed flush against the top of the screen requires less precise aiming than one floating in the middle of the workspace. Operating systems such as Windows and macOS exploit this by anchoring taskbars, dock icons, and menu bars to screen edges, allowing users to quickly access them with minimal movement. However, designers must be careful not to interfere with other edge-based interactions, like window resizing grips, which also rely on the screen perimeter. By thoughtfully allocating edge space, we can create fast, reliable entry points for essential functions. A classic illustration of Fitts' law in action is the contrast between the menu placement strategies of macOS and Windows. In macOS, a single menu bar spans the top edge of the display, and it changes context depending on the active application. Because the top edge is an infinite target, users can move the cursor straight upward and click with minimal effort. Windows, on the other hand, embeds a separate menu bar inside each application window, typically near the top but not flush with the screen edge. This arrangement forces the cursor to travel a greater distance and land on a finite-sized target. Empirical studies have shown that the macOS menu can be selected roughly 5 times faster than its Windows counterpart, confirming the predictive power of Fitts' law. This example underscores how a simple layout decision can have a measurable impact on efficiency. The bar chart above quantifies the difference in selection speed between the macOS top-of-screen menu and the Windows in-window menu. The macOS bar, representing a predicted movement time of 0.2 seconds, is dramatically shorter than the Windows bar at 1 second. This 5-fold disparity aligns with the theoretical prediction derived from Fitts' law, where the infinite edge target on macOS reduces the index of difficulty. Visualizing the data helps designers appreciate how a seemingly minor placement choice can translate into measurable time savings for users. When scaled across thousands of interactions per day, these savings accumulate into a substantial productivity boost. Such charts are valuable tools for making evidence-based design arguments. Pie menus present options arranged like slices of a pizza, radiating outward from a central hub. When the user activates the menu, the cursor rests in the inactive center, and each slice extends outward, offering a large target area that is only a short distance away. Because the slices are evenly spaced, the user can select an item by moving the mouse in the direction of the desired slice, often without looking at the screen, a technique known as mouse ahead. This design leverages Fitts' law, the distance A is minimal, and the width W of each slice is relatively large, resulting in a low movement time. For novice users, the visual layout is intuitive, while experienced users can develop muscle memory for rapid selection. Pie menus have been employed in games like The Sims and in browsers such as Mozilla to provide efficient context actions. The pie chart compares the proportion of usable target area between a typical pie slice and a conventional rectangular button. In this illustration, a pie slice occupies about 70% of the available angular space, while a linear button consumes only 30% of the horizontal width. Because pie slices are larger and positioned closer to the cursor's origin, users experience faster selection times and fewer misclicks. Traditional menus, however, may be more familiar to users who have never encountered radial layouts, introducing a brief learning period. Designers must weigh the performance gains against the potential need for onboarding or visual cues. When implemented thoughtfully, pie menus can dramatically improve interaction efficiency, especially in contexts where speed is critical. Mouse gestures extend the concept of pointing by adding a drawing component. The user presses and holds a mouse button, moves the cursor along a predefined path, and then releases the button to execute a command. Each gesture corresponds to a specific function, such as navigating back, refreshing a page, or opening a new tab. Advanced settings allow the designer to assign gestures to any mouse button, providing flexibility for left-handed users or specialized hardware. Because gestures combine movement and click, they can reduce the number of separate UI elements needed, decluttering the screen. However, they rely on users learning and remembering the patterns, which may affect discoverability. When paired with visual feedback, mouse gestures become a powerful tool for streamlining workflows.